Hey guys, this is Professor Janacek. Want to go over a convergence test? Want to specifically look at the root test. Not going to go over why the root test works, just want to make sure you understand how to use it. First thing, we're going to look at a series. In this case, it's the sum as k goes from 1 to infinity of some general series, a sub k. Make sure that you recognize that for the root test, a sub k has to be greater than or equal to 0. So the terms of the sequence must be non-negative. Now, what is the root? How does the root test work? Well, we're going to take the limit as k goes to infinity of the kth root, that's why it's called the root test, of the absolute value of a sub k's. If that is less than 1, the series converges. If that limit is greater than 1, then the series diverges. If that limit is equal to 1, though, this test is inconclusive. Doesn't tell us anything. So, less than 1, I have a result. Greater than 1, I have a result. Equal to 1, though, going to have to use another test. So let's try some examples here. Let's begin with the sum as k goes from 1 to infinity of k raised to the k over 3 raised to the 1 plus 2k. Now, I'm not going to work with the series itself. Instead, I'm going to take the limit as k goes to infinity of the kth root of the absolute value of the terms of that series. Notice again, I'm not putting an equal sign there. That is not correct. These are not equal. I'm just looking at the limit to tell me what's going on with the series. All right, I'm going to start by playing around with those exponents there in the denominator. So 3 raised to the 1 plus 2k, that's 3 to the 1 times 3 to the 2k. All right. Also, well, so 3 to the 1 is just 3. 3 to the 2k, that is 3 squared to the k. Remember all those properties of exponents. I think I'm going to go ahead and take the kth root now. Yes, I could simplify 3 squared, and you're welcome to do so at any time. But let's jump in and take the kth root. K is an index, k is an index, k is an exponent. Those undo each other. Happens here as well. So, still have that limit notation. Don't forget to write that there. We haven't taken the limit, so we have to continue to write that. I'm going to take the kth root, though, so I don't need that radical anymore. Kth root of k to the k is just k in the numerator. In the denominator, the kth root of 3 squared to the k is just 3 squared. Notice I haven't dealt with this one. That one stays inside the radical. So that is still the kth root of 3. And I think I'm going to go ahead and take the limit now. I think that's all we need. Notice k here as an index. K gets really large. That index gets really large, which means that denominator gets really small, which means the whole expression gets really large. Also, k goes to infinity, which means that numerator gets really large. So this whole thing, by 2 counts, gets really large. It approaches infinity. That tells me that this limit since it's approaching infinity, it must then be greater than 1. Greater than 1 tells me that the series converges. I'm sorry, what did I say? Greater than 1, the series diverges. Okay, not so bad. Let's try another. Let's take the sum as k goes from 1 to infinity of 5k minus 3k cubed over 7k cubed plus 2, all of that raised to the k power. K in the exponent makes the kth root test a good choice. Again, taking the limit as k goes to infinity of the kth root of the absolute value of the terms of this series. All right, lots to write down, but it's not so difficult. Now in this case, I have k as an index, k as an exponent. Those undo each other. And so we end up with just taking the limit of the absolute value of 5k minus 3k cubed over 7k cubed plus 2. All right, now how do we take this limit? Well, not going to use L'Hopital's. Do not use that. We can use this little technique that we have for rational expressions. Going to look at the degree of the denominator. In this case, that's 3. So if I simply multiply by 1 over k cubed over 1 over k cubed, things should simplify nicely and I can take that limit. Notice I am putting that in the absolute value, but k goes to infinity. It's going to be positive, so adding those absolute values is not going to be a problem at all. All right, so next all I'm going to do is I'm going to just simply take these and distribute them in there. When we do that, still have that limit notation, don't forget about that. We have now the absolute value of 5 over k squared minus 3 over 7 plus 2 over k cubed. Make sure you get all that. All right, now we can take the limit as k gets really large, k squared gets really large, which means 5 over k squared gets really small. Same thing with k cubed, that's going to get really large, so 2 over k cubed gets really small. Really small means the limits go to 0. So we have 0 minus 3 over 7 plus 0. Still in the absolute values, but we can simplify that down. And our result we see in this case is less than 1. Less than 1 tells us that the series converges. Not too bad. Let's see if we can make this a little more challenging. Let's try the sum as k goes from 3 to infinity of negative 12 raised to the k over k. Now I know that doesn't look all that difficult. It's kind of simple compared to the one we just looked at, but you'll see why I say this could be a bit more challenging. Let's take a look at the limit as k goes to infinity of the kth root of the absolute value of those terms. That's negative 12 raised to the k over k. All right, well, I do see that I have k as an exponent and k as an index, so I'll go ahead and put those together. Still write that limit notation. So we have negative 12 in the numerator. In the denominator, though, I still have a radical. It's the kth root of k. Right, not too bad. Let's see. I'm going to go ahead and factor out that 12 in the numerator. I could do this a couple of different ways. I'm going to go ahead and just factor it out. I'll leave it in the absolute values for now. I'll take it out here in a second. You can write it either way. All right, and so in the denominator I have, let me go ahead and write that as k to the 1 over k power, right? All right, so let's do a couple more things. Absolute value of negative 12 is 12. K to the 1 over k in the denominator is the same as k to the negative 1 over k in the numerator. All right, okay. Whew, all right. Still mostly just some algebra, remembering how to work with exponents and whatnot. So how do I deal with that limit? Okay, here's where things get challenging. Notice I have a k in the exponent. I have my variable in the exponent, and I want to take the limit of that. So I'm going to use this property of inverse functions. This is again a technique you might have seen in Calculus 1 when you first started looking at limits. Really kind of nice idea. Might have also used this a little in algebra. I'm going to use e to the natural log of that argument. So notice this thing here is here in the argument of my natural log. I'm using the property that e and the natural log are inverse functions. All right, so what can we do with this? Well, turns out I can do a couple of things. Let me go ahead and start with moving that exponent to the coefficient location. That is a property of logarithms, right? Exponent moves to the coefficient. Okay, well, let's clean that up a bit, just so everyone sees where everything is. This is negative natural log of k over k. So the k is in the denominator, natural log of k is in the numerator, the whole thing's negative. All right, now, properties of limits, again, kind of a Calculus 1 idea, allows me to rewrite this where I take the limit of the exponent. This has a lot to do with that function e. Really kind of helps me out here. Take a moment, make sure you understand what just happened, right? That limit was out here in front, but now it's just up there in the exponent. Okay, how do I take that limit? Well, I am going to go ahead and use L'Hopital's rule. Keep that limit notation up there. But now I'm going to take the derivative of the numerator. The derivative of the negative natural log of k is negative 1 over k. And the derivative of just k is 1. So I'm simply taking the limit of negative 1 over k. Can you read all that? Let me make sure that's legible. All right. Okay. Whew. And we're practically there. All right, we've gone through the hard part. Those last couple of steps, that was the tricky stuff. Now, k is going to infinity. So 1 over k gets really, really small. Yes, it's negative, but I'm taking its absolute value, so it becomes positive. But that doesn't matter. In either case, it goes to 0. Check this out. That gives me 12e to the 0. And 12e to the 0 is just 12 times 1, which is 12. And we recognize that that is greater than 1. Greater than 1 for that limit means the series diverges. Whew! I know that was a doozy. Hope that all made sense. Enjoy.